Welcome back, guys. We're now looking at exponential functions, something that we've seen, I guess, earlier in the year, quite a couple of times. And so exponential functions look like uh, either going up, down like that way, or we could have something that goes like that as well. And so what we have is exponential growth and we have exponential decay. Okay, so obviously it's exponentially increasing or exponentially decreasing. The function for exponential growth would most likely be um, something like, say, a of x, okay, where we have this base of a, and then the exponential decay is going to be represented as the function of x, which is a 1 over a to the power of x, or you could have that a to the power of negative x. Okay, so we've kind of touched on this in previous chapters, looking at how the manipulation of x and variables of a would actually affect the certain graphs. And you would also be familiar with this structure in interest. So when we did financial maths. When we looked at compound interest and simple interest, this is basically the form of exponential growth or decay. So if we thought about, I guess, interest rates, you've got your initial amount, which is multiplied by 1 plus or minus, and then your rate over 100, and to the number of years. And that's going to be, so your final amount, A0 is going to be your initial amount there multiplied. So when we're looking at exponential growth, exponential functions, what we can do is we could actually just replace some of these values with just simple variables, which is k a to the power of x. Okay, so y is equal k a to the power of x, where k is going to be representing the initial value or initial amount, and then a is going to determine if it's going to be growth or decay. Okay, so you could see that I guess just if in terms of connection to financial maths, so a is the initial amount, which is what we're replacing with k. The 1 plus or minus the rate, interest rate, R over 100, is going to be determining growth or decay, and then we're representing that as the base A. Okay, there's their connections there. And we'll just quickly go through a few examples just to, I guess, revise this topic that we've covered in the past. So we have, let's say, a number of bacteria. We're going to represent as n in a petri dish. And we'll have after, say, so the number of bacteria, n, in a petri dish after x hours is given by the equation. So we've got the equation of n is equal to 50 times 2 to the power of x. Okay, and so that's going to be our exponential equation or function here. The initial number of bacteria in the petri dish, so A is looking for the initial amount. So initial amount is when x is equal to 0, okay? And so what we'll do is n is equal to 50 times 2 to the power of 0. Anything to the power of 0 is just 1. So that means there is the number of bacteria that actually exists in the petri dish at the very beginning is 50. All right. But then if we say after 3 hours, obviously then our function is going to be, I guess, f of 3. f of 3, which is basically 50 times 2 to the power 3. 8 times 50 becomes 400. Now, if you were asked to graph this, so here we have our x and y axis. This is going to be the number of bacteria. This is going to be the time. So we'll say 1, 2, and 3 hours. And then what we have is, let's say 1, 2, 3, 4, 500 as our scale. We know at 0, we're at 50, and then at 3, we're at 400. So we're about there. And because we've got exponential growth, we've got something like that. Okay. Or what you can do is we could essentially make it a little bit more accurate by substituting f of 1. F of 1 is going to be 50 times 2 to the power of 1, which is going to be 100. So at 1 hour, it's at 100. If we have f of 2 at 2 hours, it's going to be 50 times 4, which is going to be 200. Okay, so 1 to 200 is here. And then you can join the dots, which looks like that. That's a rough sketch, but you get the idea. Another example, reverting, I guess, back into finance. We have a new computer worth $3,000. And then obviously after each year, it's going to depreciate in value. So loses value, let's say 12% compared to the previous year. So that's our annual depreciation. Determine the value of V of the computer after the first year. So what we'll have is, obviously the initial amount is going to be 3,000, but if we're going to say after the first year, basically 12% loss is you're going to be left with 88% of 3,000. Okay, so 0.88 is in decimal form, multiplied by 3,000, you'll end up getting, say, $2,640 as the value after 1 year. Okay, and then if we continue this process after the second year, so basically V of 2, we're not starting at 3,000, we're starting at 2,640. And what we want is again, we've lost another 12%, so we're going to do exactly the same thing, 0.88 times 2,640, and after the second year, we'll end up having $2,323.20 as the, I guess, the value after 2 years. But because you already know that what we're looking at is, I guess, your final amount is going to be your initial amount, 1 plus or minus r over 100. N is going to be determining the number of years. In this case, we apply the same thing, so 3,000, and then the rate is 12. If r is 12, so 1 minus 12% is actually 0.88. And then n is going to be the number of years. So what you can do is you can just put that as your formula, just going back to compound interest and applying the same rules. So if we wanted, say, the value after 10 years, we simply have 3,000, 0.88 because it's depreciation to the power of 10. Put that into your calculator. The value is going to be $835.50 after that. Okay. So I want to finish off with one last question. And again, just using the data that we have and the formula that we're working with of P is equal to Ka to the power of X. we can solve this. So basically, let's go through this. Assume that the relationship between population P and the year X can be modeled by the function of that, where X is the number of years after 1985. The value of P must be multiplied by 1,000 in order to find the actual population. Okay, but they've abbreviated that simply just to make the numbers a little bit easier. So there's the population of a certain city, and we have got a table as shown. So for question A, the state of the value of K, the initial amount, okay, is going to be 128,000, all right, or just 128. In this case, it's going to be assume that it's going to be multiplied by 1,000 already. Okay, so then the next thing is to use the middle point in the data set to find the value of A. And let's say the middle point is 1995. So from 1985 to 1995, we're looking at 10 years. So we're looking at when X is equal to 10. All right. We know that the initial value or initial population is 128, and we know that when X equals 10, that the population is equal to 232. So we'll put that into our formula. So 232 is equal to K, which is 128 times A to the power of 10. So now that we've populated all the variables, we can now just work out what A is. So we'll have A to the power of 10 is equal to 232 divided by 128. And so remember, and to get A on its own, when we want to get A on its own, we want let me write this clearly, we want the 10th root of that fraction. So 232 over 128. So just on side note, if we want to square something, to do the opposite of that is going to be the square root. So A is equal to 2. If we had, say, a to the power of 3 is equal to 27, then what we want to do is the cube root of those things to get the answer of A. So from doing the same principle here, to get A on its own, we want the 10th root of that fraction, and that's going to become, let's say, it's about 1.0613. And so what we could do is we could simplify it to, say, 2 decimal places to 1.06. So now that we've worked out what A is, our actual formula for the population is going to look like P is equal to 128, 1.06 to the power of n. N is going to be however many years. Okay, or what we could do is power of x, same thing, because I guess we're going to just make it a little bit more consistent with the narrative here, where x is the number of years after 1985. So with question C, it's just asking to use this formula to, I guess, repopulate the table up the top. So if you end up having the population is 128, 1.06, obviously it's abbreviated, say to the power of 0, that's going to remain as 128. If we then decide to put, let's say, 5 years, because that's going to be 1990, then through this formula in the calculator, we end up getting 171. So it's slightly off, but it's very, very close in to what was initially indicated. If we ended up having 1.06 to the power of 10, which is the 10 years, we end up getting 232, which is great. P to the power P, the population of 128 times 1.06 Now, if we're looking at the year 2000, we're looking at 15 years. So we're going to apply that to the power of 15. We end up getting 300 and... Sorry, this ends up being 229. 307, slightly going off a little bit more. And then if we go all the way to, say, 2010, which is, what's that, 25 years. So putting that into your calculator, to 25 years, you'll end up getting, say, 549. So some of the values are a little bit off, but that's because our value for the base A has been, I guess, approximated and rounded off. So hopefully this has been a good refresher to exponential graphs, growth and decay, appreciation and depreciation in financial maths. And if you have any questions, let me know. Otherwise, see you in the next video.